Thank you, everyone. I will be presenting this work that was done by the two Laurettes, we sometimes called. The work is on exploiting a multilingual semantic machine translation architecture for knowledge representation, and specifically knowledge representation of patient information recorded during a screening consultation for COVID-19. I'll introduce the work, give some context, and then briefly give an overview of the speech-to-speech architecture. Then I will explain how the semantic interlingua works for natural language before showing how it can be exploited for knowledge representation. South Africa is a multilingual society with 11 official languages. English, however, is the language in which most healthcare providers or HCPs are educated in South Africa. Of course, many South Africans are not proficient in English, and this creates a language barrier to healthcare in many settings. For example, at hospitals and clinics, it is often the case that other staff, even security guards and cleaners, are called upon to interpret if the HCP and patient do not share a common language. This obviously has a detrimental effect on efficiency, on patient privacy, and on the ability of HCPs to provide respectful care. The COVID-19 pandemic has really shown how necessary it is for healthcare systems to be able to cope with enormous amounts of patients at once, and it has also highlighted the need to be able to record information that would help us understand and respond to dangerous viral outbreaks. Both these factors, coping with lots of patients and recording patient information effectively, are severely affected if language barriers exist between HCPs and patients. In order to enable screening of patients for COVID-19, a speech-to-speech mobile translation application was developed or adapted, which translates spoken English utterances to spoken utterances in all other official languages of South Africa. The app, called Aweza Med COVID-19, uses automatic speech recognition, or ASR, grammar-based machine translation, and text-to-speech, or TTS. In this paper, we describe how Aweza Med COVID-19 could be adapted for knowledge representation within existing KR frameworks. Specifically, we show how the existing translation architecture can be exploited to enable HCPs to seamlessly record patient information during a screening. I will quickly introduce some of the core technologies harnessed in our work. The need for interoperable patient information is well known, and many existing technologies have been developed to address it. This includes, for example, the SNOMED clinical terms collection, OpenEHR, and the HL7 and FHIR standards. OpenEHR is a technology for creating and managing electronic healthcare records, or EHRs. It consists of open specifications, clinical models, and software that support the building of information and interoperability solutions for healthcare. OpenEHR makes use of a two-level model consisting of the reference model, where data types and data structures are defined, and then the archetype model, in which domain knowledge can be described. The goal of the archetype model is to allow clinicians to develop formal models that reflect their domain knowledge. Such models can take the form of archetypes for modeling healthcare concepts and templates for modeling forms, documents, and messages. The so-called clinical knowledge manager serves as a platform where clinicians can share and collaborate on archetypes and templates. For example, recently an archetype for COVID-19 symptoms was contributed, as well as templates for modeling clinical processes related to COVID-19. Semantic web technologies allow the creation of data stores on the web, the building of vocabularies, and the writing rules for handling data. Linked data are supported by technologies such as RDF, Sparkle, OWL, and SCOS. In RDF, a description of a resource is represented as a number of triples, each of which codifies a statement about semantic data. As the abstract model of the semantic data model of the semantic web, RDF is considered one of the dominant graph technologies currently driving semantic computing over web-scale distributed data. And then finally, Grammatical Framework, or GF, is a programming language for grammar engineering. It uses semantic interlingua for multilingual machine translation, and it has become the de facto standard in multilingual controlled natural language applications. The architecture chosen for the speech-to-speech translation app depended on a number of factors. In terms of machine translation, two paradigms exist, namely data-driven MT and rule-based MT. The former tends to be a better choice if wider coverage is a priority, while in the South African context, the latter tends to be a better choice if accuracy is more important. Obviously, in the medical domain, accuracy is crucial. Another factor to consider was the integration of the MT component with ASR. Rule-based language models, which are by nature more constrained, result in significantly better ASR performance in the acoustic environments of hospitals and clinics. Finally, the limited roles and responsibilities of the different roles and responsibilities of the participants in the screening, namely the HCP and the patient, were considered. Utterances of an HCP who drives the communication during screening is more structured and predictable, while those of the patient tend to be more free. HCPs are domain experts who have a clear goal in mind during a screening, whereas patients are laymen who typically relate experiential knowledge. And of course, the HCP has a responsibility to provide respectful care and therefore has a heightened responsibility to communicate accurately. Taking all this into consideration, it was decided that the application would focus on communication by the HCP to the patient in such a way that only yes or no answers, verbal or via gestures, would be required from the patient. A rule-based, or in this case a grammar-based approach, was followed where coverage is constrained but the accuracy is high, both for ASR and MT. Grammatical framework is a grammar engineering framework that makes use of a semantic interlingua. It can be thought of as a multi-source, multi-target compiler for natural language. Translation is achieved by parsing into an abstract syntax tree via a concrete syntax for the source language, and then linearizing into text via a concrete syntax for the target language. A multilingual domain grammar attempts to translate domain-specific utterances with high semantic accuracy. One starts by defining the semantics of the domain in an abstract syntax, and then for each language you define a concrete syntax which expresses the meaning of the abstract syntax in each language. If the domain grammar is deployed in the right context, translation will be grammatically and semantically correct. So how does this look? Here we have an example of an abstract tree that encodes the meaning of, did the fatigue start about 2 days ago? The figure at the bottom left shows a semantic parse tree where each token is connected to the semantic category that it originates from. In the bottom left, we can see the same semantic tree expressed in isiZulu. Note the difference in capitalization and punctuation. In the English case, it corresponds to the conventions for ASR output, while the Zulu corresponds to typical written conventions which a TTS system would expect to receive. We can go further than linearizing the semantic tree into natural language. It can also be linearized, marked up in such a way that the different strings in the utterances can be used to populate dynamic screen elements. These screen elements can be updated as the user makes selections. The images here show a section of the app screen representing a so-called dynamic utterance. A set of trees is implicitly represented here with clickable elements that the user can select from to change the utterance. Alternatively, the user can speak an utterance supported by the grammar and the screen will update accordingly. To see how the grammar powers the screen content of the app, consider the green blocks that are in fact buttons. If the user would, to give a simple example, click on 2 in order to select 1, the string days would automatically change to day, as the semantic tree is updated in the background and along with it, its various linearizations. It is this broad notion of multilinguality that we exploit in this paper to achieve knowledge representation. Since each tree in the application represents a binary question, such as did the fatigue start about 2 days ago, it can also be thought of as representing a statement, namely, the fatigue started about 2 days ago. This is a piece of information that is typically captured in health records. For example, in the context of OpenEHR, the tree shown here represents an observation corresponding to the COVID-19 symptom archetype and making use of the SNOMED CT vocabulary. OpenEHR uses JSON among other formats to encode information. So here we would want to generate JSON code. Excuse me. Similarly, the tree can be thought of as representing a set of RDF triples using the FHIR ontology and SNOMED CT vocabulary again. In this case, we would want to generate the correct turtle code to represent the information. In GF terms, therefore, what is needed is 2 new concrete syntaxes for OpenEHR and RDF respectively that would enable the GF runtime to parse and linearize meaningful JSON and turtle code. And here is an example of the code generated in this way. Although we don't have parse trees, the color coding shows that various parts of the strings that were generated originate from nodes in the tree. So what we now have is a representation of the semantic tree in various natural languages, as well as 2 knowledge representation paradigms. Let us consider the user experience implications of this. Each binary question on the screen implicitly represents a statement of fact, and the HCP would be able to use the speech-to-speech application to establish such facts about the patient. If a button is added to the application screen, which allows an HCP to indicate any question as confirmed, recording of patient information could be done with a single click per statement. This is in contrast to inputting each meaningful concept in the semantic tree, in this case, the symptom and the onset time, and actually the relativity of the onset time as well, via more traditional screen elements such as drop-down boxes and calendar widgets. To conclude, we started with an existing speech-to-speech application which was designed to meet the requirements of a specific use case. Namely, it covers a limited domain but with high accuracy, and it enables conducting a screening procedure via binary questions put to the patient. Because the translation architecture is based on a semantic interlingua, it could be exploited for knowledge representation. Furthermore, this could be done in a way that integrates seamlessly with the existing UX of the application. Our proof of concept implementation covers 396 unique utterances. We implemented 4 utterance types, which reference 12 COVID-19 related symptoms, 3 different ways of expressing relative time, and 10 small numbers for counting days. In order to implement this in a real-world concept, however, 2 next steps would have to be taken. Other utterances supported by the grammar should be analyzed, and the concepts they express must be associated where possible with existing knowledge representation concepts, whether it's archetypes or ontology concepts. In cases where the necessary terms, classes, properties, and constraints do not exist, ontology development is required. Then, of course, the application must be extended to deal with real patient information records and link to real patient information repositories. Thank you.
Okay, so I don't see any questions yet, raised hands or questions in the chat box, but thank you so much, Laurette, for a very interesting presentation. Let's just give another few minutes for questions. The floor is open. Any questions?
We have time, so please take your time. Sorry to just chip in, but I don't want us to be too far ahead of the program because people sometimes come just for one talk. So if there